Good day and welcome to this third video in this short series on heuristic optimization approaches for project selection on multiple network elements. There are two preceding videos which you have to watch before you watch this one. I'll put the link to those videos in the description below, and that will explain to you basically how we have structured our problem, what is the toy problem that we are using to explain these concepts, etc. So previously we looked at this approach which we called the bottom-up greedy approach, and then next we looked at the bottom-up egalitarian approach where we spread the projects more evenly amongst elements on our network. And in this approach, in this video, we're going to deal with a third approach which we call the bottom-up decreasing incremental benefit cost ratio method. Now before we go on to look at the details, I just want to explain one underlying element which is specific to this method. In the first video we explained the concept of a Pareto front, which you can see again here. And here we are looking, just to clarify again, we're looking at projects. Each blue dot is a project, and all of these projects relate to one network element. So these are project candidates on one road or one bridge on a network. And the Pareto front is these projects which are not dominated. They are always better than any of the projects that lie outside of this region. And we mentioned that, as explained in this research paper here, that projects which lie on a convex section of the Pareto curve are generally locally preferred solutions, while those that lie in the concave section, like area B, are locally poorer solutions. However, when we have a budget constraint, and specifically if we've got a categorized budget, we don't always want to just neglect these solutions, right? But now in this third approach that we're going to explain, the approach assumes for a starter that we are not using this Pareto front, but we are only using projects on the convex sections of the Pareto curve, which means that we will always go in a way that the incremental benefit cost slope gradually reduces. And that means we're basically going to draw a line between this region A and that region A, and all of these projects will be taken out of consideration, right? And so if we go and look at the problem that we discussed in the previous videos, I'll go to this sheet called bottom-up decreasing incremental benefit cost ratio. And first of all, this is our original problem that we explained in the previous two videos. And you can see in this problem, I've got some projects which have got a Pareto front with a concave region. So for us to use this method, we first have to take that project out of consideration. And similarly on this blue curve, I have to take that project out of consideration. All of the others have a convex Pareto curve, so that is okay. So we prepare our problem by taking out those two projects, which I've highlighted here in red, because they cannot be considered in this decreasing incremental benefit cost ratio method. So after taking out all of those projects, I get this reduced problem here. Right, this is my reduced problem, and you can see if I plot these curves, now I've got only convex Pareto curves to consider, and therefore I'm not considering that project at all, and I'm not considering this project. So having done that, the next thing that I'm going to do for this problem is so for this problem I'm going to take all of this data. I'm just going to copy out each of these and put them one below each other in a table like this. So these are all my projects. Noted that I've updated my incremental benefit costs, because these costs here no longer apply because I've skipped this project. So this project's incremental benefit cost is now going to change, as you can see has happened there. Okay, so I construct my list of projects like this. And then I've just copied them over here, and I am going to order this list by a decreasing incremental benefit ratio. So basically I'm going to walk up this curve with all the projects being considered at the same time. Okay, so here I've got my table, sorted by decreasing incremental benefit cost ratio. And notice that these elements here are the do nothing projects, so I cannot really select them in the true sense of the word, so I'll just highlight them there. And I'm going to start by picking the project at the top with the highest incremental benefit cost ratio, and remembering that I can only pick one project per element. So I'm going to pick that one, and that one. My budget is, I've got one picked on every element except C, and my cost is still lower than my budget, so I can change this project on E to a better one. So I make that a 1 and I make that a 0. Now I'm going to change A, so I make that a 1 and I make that a 0. My budget is still acceptable. Now I make this one a 1 on C, and that's the first time C is entering, so I don't have to take anything else out. Now I'm going to try and change this one on B, so I make that a 1 and I have to remove that one. And now I can move C up again. I make that a 1 and that a 0. And the next one is to move B up yet again. So I move that a 1 and I take that a 0. And this gives me a cost of 56, which is still below my budget. So I've got two more projects that I can consider. I can change this one of A with that one. So I'm going to make this a 1 and that one a 0. But my budget is exceeded, so I cannot do that. But I can try this one. So I can make that a 1 and then take this D out of commission, 0. That also busts my budget. So I also have to rewind that. And this gives me then my optimal solution. I've looked at all the candidates, and you can see I get again the same cost and benefit as I got with these other two approaches, 56 and 552. However, as I mentioned in the earlier videos, this approach is yet again something different, because we have discounted some projects here that do lie on the Pareto front, but they do not have decreasing incremental benefit cost ratios. Right, so the different approaches that we have here really can give different answers. For this toy problem, they gave the same answer, but it is not always the case. So just for showing this in Juno Cassandra, I've put all of the data here in a sheet. I've put just treatment. I'm not using a categorized budget here, so it doesn't matter what the treatments are. And I have just quickly run this in a little benchmark framework that we've got for testing our algorithms. And you can see if I run this through the JCass algorithms, if I do the low to high cost egalitarian, I get a budget of 67. My budget is 67. I get 56 cost with a benefit of 552, 5 projects picked. And my for the next, the high cost greedy, I've got the same answer, and again for the decreasing incremental benefit cost ratio, I also have the same. So in this case, the answers are all the same. However, if we have a much bigger project with a stratified budget, where we've got budgets in different cohorts, these different approaches will give different answers. And I'll just show you an output here for a problem which is much more realistic, with several hundred elements on a road network and different projects for each one with a categorized budget. And I'll show you what the results for that look like. So here is an output for a more realistic problem. So just ignore this budget number here. What I've actually given here is a categorized budget, and I've allowed for seal type projects 4 million. I've allowed for rehabilitation projects 10 million, and for asphalt concrete projects I've allowed 3 million. So you can see I've got my 3 different approaches here. My low to high cost egalitarian approach picks 167 projects, The budget constraints are met, and my benefit is 55,047. If I take the low to high cost greedy algorithm, this picks fewer projects, as we will expect, because this egalitarian one spreads the projects around much more, and this one gives me a slightly higher benefit of 55,942. And you can see here how many sealed projects. This one picked fewer sealed projects. It picked slightly more rehabilitation projects and slightly less AC projects. Right, and then the last one is on the decreasing incremental benefit cost ratio, which we've just explained in this video. This one picked 146 projects, so slightly less than this one for this specific problem. You can see the budget constraints were again honored, and this one gives almost the same as the low to high cost greedy algorithm at 55,938. This one performs slightly better, so probably 95% of the projects picked by these two approaches are the same, but the one or two projects was changed, and that gave this one a slightly bigger benefit. Now, the type of optimization algorithm that you will pick depends on the approach, what you want to achieve, whether you want to treat more elements for the same budget or fewer elements. But in each case, you will be selecting, based on your budget constraint, the overall optimal for your conditions that you want to be met. So these are different approaches, there's different ways to skin a cat, so to speak, and these are all tools in the toolbox of Juno Cassandra that you can use to make sure that your funding is properly allocated to meet your specific needs for your network. So that is just the details on how we approach this currently in Juno Cassandra. We are working on two different algorithms which we're still testing to see if they can outperform any of these three ones, and over time they will also be added to the Juno Cassandra framework. So that's it for this video. Thanks for watching.